Welcome you to this video lecture where we discuss time response. Last time we discussed in previous video about time response, and we basically overview second order response, and then we come out to this S-plane where we discuss how poles behaves when you have different location in S-plane. So the main point that we get from this S-plane behavior, that if you are near the origin you have a sluggish response. So if you move away from the origin you have fast response. So thing is that if you are near origin, so your response is slow, and normally we use word sluggish response. So if you move away you have very fast response. Now question is, if we are getting very fast response, why we care about the slow response? The thing is, as you go away from here in this direction, your response is fast, but for fast response you need very big actuators to achieve that response. So this is not always possible. So we have to make a compromise with realistic and this one actual the ideal one, that we want the fastest response, but we have to be very realistic that can we have this type of actuators available with us or not. Okay, now we will continue this, and from here we discuss the general second order system. So we just generalize how second order system look like. So first thing that we discuss is known as natural frequency. Okay, natural frequency. So in natural frequency we normally represented by omega n. So what is natural frequency? The frequency of oscillation of the system okay, the frequency of oscillation of the system without damping. So if we remove all the damping from the system and then let the system to oscillate, that frequency is known as natural frequency. Okay, so the next thing that we need to know is the damping ratio. Normally represented by a zeta, something like that. So actually what is zeta actually? So to identify what type of damping we have, normally we calculate zeta as ratio of exponential decay exponential decay frequency divided by natural frequency. Natural frequency that we discuss that is in radian per second. So this actually equal to 1 over 2 pi natural period, you know that is calculated in seconds, divided by exponential time constant. So this is the ratio that tell us about the damping of the system. So there are two important properties of general order system. One is known as natural frequency, other is known as damping ratio. Actually, damping ratio is a variable to quantify the damping actually. Okay. Now, if we write a transfer function of a generalized second order system, that is g of s equal to b divided by s square plus as plus b. Okay, so this is a second order system. Now, without damping, means that your poles would be on the j omega axis. So if there is no damping, so in that case your pole is on j omega axis. So this is only possible if your a0 in g of s. So if a is 0 in g of s, so in that case your transfer function look like b divided by s square plus b. So this is the transfer function if I calculate the pole location. So here pole location come out to be s is equal to plus minus j under root b. So that tell us that you are at the j omega axis, or in other words you are undamped response, or you have a pure oscillations. So by definition the natural frequency is the frequency, if you remember, is the frequency of oscillation when there is no damping. So this means that, this implies that omega n is actually, this is the frequency, because we know that s is equal to j omega and this is our frequency. So if we compare these two, so from here we know that frequency is under root b. So this is the natural frequency, or in other words we can say that b is equal to omega n square. So these are the formulation that we can get. So as you remember, we discussed the damping ratio. How we defined the damping ratio? In previous slide we defined that damping ratio is equal to exponential decay frequency. Okay, and exponential decay frequency is actually depends upon epsilon, that is sigma, magnitude of sigma divided by omega n, or in other words is equal to a divided by 2 divided by omega n. Okay, why it is that? Because if you look at the equation here, so you have a small a. Okay, now assume an underdamped system. The complex pole has a real part that is equal to minus a by 2. How we get it? Just let me write here. So this is our system, s square plus as plus b equal to 0. Now if I write the roots of this becomes minus a plus minus a square minus 4 b whole divided by 2. Okay, so if this is a what you say complex part or imaginary part, so this becomes the real part. So from here this is, so this give us the exponential decay, and this is the oscillation. So that's why it is exponential decay magnitude divided by so, and the epsilon or real part becomes minus a by 2. So if I take this, and so from here we calculate the damping ratio, that becomes a divided by, or in other words we can say that small a in the equation say 1, in equation 1 small a is equal to 2 zeta omega n. Now we know b, we know a. Now if we instead of a b we put omega n square here, instead of small a we put 2 zeta omega n. So this gives us a generalized second order transfer function, that is omega n square, or divided by s square plus 2 zeta omega ns plus omega n square. So this is the transfer function. So this is the generalized second order transfer function. Okay. Now let's look at an example here. So this is an example. It says that find zeta and omega n. So transfer function given you is 36 divided by s square plus 4.2s plus 36. Now on comparing how we solve it, so for solution we said on comparing with second order standard form, that implies that 2 zeta omega n equal to 4.2. This is equation 1, and for equation 2 we have omega n square equal to 36. Now from here this is equation 2. Now from 1 and 2 omega n becomes 6, and when we put 6 in this equation, from here zeta come out to be 0.35. So this is the way you can calculate zeta and omega n from second order dynamic systems. Now we will move further. Now we just overview what we discussed. Okay ji, and now let's look here. They are very important things. So we can have two basic things. One is omega and other is zeta. So this means that for second order system we have two pole locations. First is zeta omega n and plus minus omega n under root 1 zeta square minus 1. So square minus 1. So it's better. There are two ways of writing. I can write zeta like this or this, so sometime like that. So it's better. This is the form. So let me rewrite this so that it's written correctly. Zeta and zeta square minus 1. So actually for this what you say roots location or pole location, so these are poles of second order system. Now if I look at different values of zeta, so damper ratio, okay, and then look the poles, how poles look like, then look at the step response, how step response look like. So if I try to see this, for example, assume that if zeta is 0, so this means that your poles, because there is no damping, pole is at j omega axis. We already discussed this thing. So this is my S plane actually. So this is real part, this is j omega part, Now it is at j omega axis, so this is my S plane. Okay. Now because this is undamped system, so you have pure oscillations, something like that. Okay. So this is undamped. This means that undamped response is when zeta equal to 0, and this is your response C of t, and this is t tends to infinity. Now the next one, if we say that zeta is between, it's greater than 0, okay, less than 1, so in that case how my roots look like. So I told you that we are looking the stable system, so this is j omega, this is my sigma, and this is my S plane. Okay, now you have something here, so you have some poles at j omega axis, so this point is actually minus zeta omega n, okay, because this is the real part and this is the imaginary, that is omega n under j times omega n under root zeta square minus 1. So this is the imaginary part. Okay. Now if I look at the response, so this is under damped system, so it means that if this is my C of t, this is time t, so in that case if I want to give a step input to the system, and this is the behavior I note with the step input. So this is underdamped system. Alright. So we wrote here underdamped system. So underdamped system has overshoot, and here undamped system is pure oscillations, and these are the pole locations. Now the one we discuss is zeta equal to 1. This is known as critical damp. This is only possible in S plane if you have a roots both on the real axis. So look here, so these are both at j omega n. Okay, so this is the pole location. Now if we look at the response, and this is my t, and this is C of t. So if I look at the response, this response will look like this, if this is my step input. Okay, so this is known as critical damp. So it has no overshoot, so overshoot is 0. So this is known, so in critical damp, so main idea is that you have two real poles or repeating real poles. Okay, now the last one is when zeta is last possibility is that your zeta is greater than 1. Okay, so in that case you have a system with real poles, but those poles are not repeating, so this is S plane. You have two poles. Okay, so if you look at the poles, how these poles look like, so these poles look like something minus tau omega n and plus omega n under root zeta square minus 1. Okay, similarly these roots look like minus zeta omega n minus omega n zeta square minus 1. So if I look at the response for, this is the response I can get, so this is our damped response. So it is try to reach the 1. If this let me, so it is start from here, and so this is C of t, and t tends to infinity. Okay, so this is the response. So these are the behavior that we can get with different values of zeta. Now we will